Jai Hind and welcome all. I am Professor Devendra Singh, taking the course on the machine design, and this is our fourth lecture in this module. Earlier lecture, we have discussed about the introduction of machine design, design cycle, design procedure, selection of preferred sizes, BI's designation of steels and alloy steels, and during the discussion we have understood, we have discussed that for a successful designer there are few things we always remember. The design whatever we make, it should be economical as well as safe. So, this is the basic philosophy for the machine design, and for economy we have discussed about the standardization that increase the reliability, that provides the opportunity to mass production, that will ultimately affect the cost of the product. Then we have also discussed about the preferred selection of preferred sizes, by which we can optimize the number of models for any product that can fulfill the requirement of the human beings of the society. That helps a designer to take some good decisions and to make the design successful for the purpose. Now, in this fourth lecture, we will start with the selection of materials, the basic criteria that we have touched in the last lecture. So, and then we will discuss about the material properties and various types of the loads. So, slowly we are moving towards the design to understand the design against strength. So, the outline of this lecture is basic criteria for selection of materials. What are the basic criteria that we have discussed? We have touched in fact in the last lecture. Today, we discuss in a little bit detail. Then stress strain diagrams we will discuss, and we will try to understand what you can get, what information, what inference you can make. आप स्ट्रेस स्ट्रेन डायग्राम देख के क्या पता लगा सकते हैं, उस बारे में कुछ बातें करेंगे. एंड इम्पोर्टेंट प्रॉपर्टीज ऑफ मटेरियल्स फॉर strength design point of view. Then various types of the loads which we come across during the practical application. So, these are the basic 4 points we are going to discuss today. Now, the basic criteria for the selection of materials are the availability. This is essential. This is essential. If material is available, then you can make any product. If material is not available, it cannot be converted the idea into the real time or the actual product. So, first of all material must be available, and now the availability, we should try to select the material which is available as nearby as possible. जितना नज़दीक हमारे मटेरियल होगा, उतना हमारा प्रोडक्ट फाइनल, हमारा जो डिज़ाइन आइडिया है, जो रियल फॉर्म में आने वाला है, जितना नज़दीक हमारे पास मटेरियल मिल जाएगा, उतना चीप आपका वो प्रोडक्ट होगा. नो डाउट वी आर नॉट गोइंग टू कॉम्प्रोमाइज विद एनी काइंड ऑफ दी any safety, but material must be available. Material should be available in the vicinity of the manufacturing unit where you want to convert your idea into the real shape. So, this will ultimately affect the cost of the product. Next point is the cost that we have discussed. We have tried to link with the availability. As far as the cost is concerned, so there are number of cost you can think of. First of all, material is required. So, raw material cost, this is required, raw material cost. So, we should if we want to make our design cost effective, so we should select the raw material without compromising the safety. Raw material which should be इकोनॉमिकल, जो सब सस्ता हो उस मटेरियल को हम सेलेक्ट करेंगे बिना सेफ्टी से कॉम्प्रोमाइज़ किए हुए. एंड सेकेंड इज़ द ट्रांसपोर्टेशन कॉस्ट. If the material is not available, then transportation cost, we need to transport the material from the place where it is available, because ultimately we need to create some product for fulfill the requirement or need of the human being. So, transportation cost will be included, and now the raw material after transportation is available. Now, we need to convert this raw material into the finished shape. So, third is the manufacturing cost. These are the primary thought I am discussing here. There we can think some other factors also, some other costs. If with transportation, it will include some charges, etc., some taxes. Manufacturing cost, the material should be easily manufacturable. The material should be suitable for the manufacturing processes you have designed for that particular product. जिस तरीके का जो मैन्युफैक्चरिंग प्रोसेस आपने डिज़ाइन किया है, जो मैन्युफैक्चरिंग प्रोसेस हम इस्तेमाल करने वाले हैं रॉ मटेरियल को फाइनल प्रोडक्ट में कन्वर्ट करने के लिए, मटेरियल में वो खूबी होनी चाहिए, मटेरियल में वो प्रॉपर्टी होनी चाहिए जिससे वो आसानी से कन्वर्ट किया जा सके. सो इफ़ मैन्युफैक्चरिंग इज़ कॉम्प्लेक्स or manufacturing is tough, then we need some special arrangement, some complexity in the manufacturing. If some specialized persons are required, then the labor cost and the skilled labor is required, that will also include. So manufacturing cost will also affect the final selection of material. So, material should be such which should be suitable for the manufacturing process, which is suitable for the idea to convert in the real time. See, manufacturing considerations that I have discussed, what type of the tolerances, what type of the limits you need to make your design or assemblies, etc. And if surface finishes, what type of the surface finish, what type of the surface hardness or case hardening or the core hardening is required. So, in fact, the manufacturing properties or welding is required or some machining is required or some forming is required. These properties we should consider when we select the material. If the material we select for which the manufacturing is not possible, or the process which we need to perform on the raw material is not suitable, then it will be it will be very difficult, if it is not impossible, it will be very difficult to get the final product. Then the material properties. These material properties, suppose if I take an example, if I need to design an impeller for a sugar industry, and the sugar cane juice or sugar or cane juice is acidic in nature, is always acidic in nature. So, if impeller I need to design for any centrifugal pump, for this impeller what material I should select? If it is acidic in nature, it will affect, it will corrode the material of the impeller, and after certain period this will be dissolved. एक हम एग्जाम्पल देते हैं, अगर हम घरों में अगर सिरका बनाए तो उसके लिए करती थी बूढ़ी अम्मा कि एक मटके में वो शुगर जूस लेती थी, उसमें एक कील डालती थी और उसे एयर टाइट कर देती थी. आफ्टर 1 month when it was filtered, जब सिरके को उसे छाना जाता था एंड देयर इज नो नेल, कोई कील उसमें मिलती नहीं थी. तो व्हाट इज इट? दिस इज समथिंग विच इज due to this acidic nature. So, if we use the impeller which is made of the ferrous material, it will have the same effect, and without any reason, after certain period the dimension impeller is to go or is to vanished. So, for that purpose, what material properties you would have to consider? The material which should have corrosion resistance properties. So, in the sugar industry you will find mostly if the copper based alloys means gunmetal or brass, though it is expensive as compared to the ferrous materials, gunmetals and brass impellers we use in the sugar industry to pump the juice from the lower head to the higher head, or from this mill house to some boiling house. So, this is the one property I have mentioned. Again, if you are designing some connecting rod, so connecting rod is subjected to some kind of tensile and the compressive load. So, what material property you need to consider for that is the endurance limit, or the or this the tensile and compressive properties. Primarily the endurance limit we need to consider for the material which is to be used for the connecting rod. So, various material properties you have to consider when when we select a material for a particular application. This is a very important and very important and wise decision taking a step for a designer. If material selection is wrong, then there is no case your design will be going to fail. So, appropriate selection of material is a very important activity in the design. Now, we start with the stress strain curve or stress strain diagram. So, this is in fact the this y axis. Here we normally place the stresses sigma, or sometimes load deflection curve. You can remember many of you have performed the test on the universal testing machine. टेंसाइल टेस्ट ऑलमोस्ट सभी को करना होता है, फर्स्ट ईयर में किया है सभी ने. स्ट्रेन, दिस इज एप्सिलॉन. So, this is the first material which is having a straight line, and it is just this is a fracture. So, what kind of material is there is no there is no considerable, or there is a very less elongation, and it reaches up to the fracture point when it is subjected to the tensile load. This is actually I have drawn in the positive quadrant. So, this is positive and this is positive. So, this case whatever I am discussing here, this is the tensile case. So, this is a brittle material. This is a brittle material. When what is a brittle material? If you try to elongate a brittle material, then it will break without a significant elongation, right. So, this is there. Second, this is having a green and it is having significant elongation before fracture or before physical failure. This is a fracture point. So, this is considerable elongation, considerable extension rate or strain, because this is strain. So, strain multiplied by length. Similarly, we can convert the stress multiplied by cross section area is the load. So, this curve can be converted into the load deflection curve, but this is considerable. So, we can elongate it. This is nothing, but this is a ductile material. What is a ductile material which can be elongated, and fracture will take after a considerable amount of elongation. this is ductile material, and this is something which is having a large elongation, and fracture will take beyond this point, and it is having a very less stress. So, this is rubber band को लीजिए, हाथ से खींचे elongate होता है, सरिये को लीजिए वो elongate होता है कि नहीं होता है, ब्रिक को लीजिए elongate होता है कि नहीं, या किसी ब्रिटल मटेरियल को लीजिए elongate होता है. तो यू कैन परफॉर्म or you can feel this is nothing, this is the amount, this is the stress which will cause this much strain, which has caused this much strain. This stress के corresponding बहुत अच्छी strain और elongation अगर load deflection curve हो तो there is a sufficient elongation. So, this is nothing but this is a plastic material which is having some flow characteristic, which when you apply a force it start to flow, and this is a plastic material. Now, the second is, this is another example. This is again stress, x, the y axis is always stress and x axis is always strain in load stress strain diagram. So, this is having a point here, and then there is a necking, a little bit addition to the brittle material, if you have seen the last diagram. So, this is the stiffest, this is the steep curve. So, there is a very less elongation and stress level is very high. So, this is called the stiff rigid material. So, this is strongest and stiffest material, means stress is more and strain is less. Then the second category, this is something which is having a fracture point here. This is a brittle material, as we have discussed, there is no necking, if you apply this fails here, this is here, this is the strain, and in case of the brittle material, the strain is lesser stress, tensile stress. Brittle materials are usually having good strength against compressive load, and whenever a tensile load applied to the brittle material, they break at a very low strain and at lower stress. Then this is a general curve, this is a fracture point, this is a ductile material, this is most ductile material, and this is, as we have discussed, this is a plastic material. So, now the ductile material salient points, this is a general curve of a ductile material, again this is sigma, this is epsilon. So, first of all this ductile material follow linear deformation and up to the point where the linearity ends, that is called the proportionality limit. P is the proportionality limit. Up to here Hooke's law is valid, up to here Hooke's law is valid. This is sigma p. So, here sigma p is directly proportional to epsilon p, and sigma p is equals to E epsilon p, where E is the modulus of elasticity. So, up to the proportionality limit, the Hooke's law is valid. So, this is proportionality limit, this is the first point. Then after that, to some extent there is a point that is elastic point. This is elastic point. This is the point up to which the material is having a capability, as soon as you remove as soon as you remove the deforming load, the material can regain its original shape. So, the point up to which this property is retained by the material, that is called the elastic limit. So, this is sigma E. The stress corresponding to point E is the stress at elastic point. After that, there is a point, this E to y, this beyond E, the material will not able to regain its original shape even after the removal of the deforming load. E से आगे जाने के बाद मटेरियल वो प्रॉपर्टी नहीं रखता है, वो ताकत नहीं रखता है कि जब उस पे से आप कोई जो डिफॉर्मिंग लोड है उसे हटा दें और वो अपनी रीगेन कर ले ओरिजिनल शेप. यहाँ से ई से वाई तक it is having a permanent deformation, but still plastic flow of the material will not happen. And then we will come to the yielding. At yield point, the flow of material will start, and there is in some materials there are the upper yield point, and then as soon as we reach to the upper yield point, then there is a steep drop in the stress level, means that it is only due to the flowability of the material. And then there is a zone where the this rearrangement of the materials, that is that zone is called the work hardening or strain hardening, and then material will again get some more resistance, and it will start, the curve will start rise up. So, next is this point u, this is the ultimate point, or this is ultimate point, and corresponding to this, this is sigma u, and if it is in tensile test. So, this is sigma u t or s u t, the stress level at this point is called the ultimate tensile strength, and after that there is a fast flow of the material, and the cross section area will start decreasing, and in fact, the stress, true stress will move like this, but the due to the flowability or due to the resistance reduced, and this is called the necking, this zone is called necking, and after a certain time the area is so much reduced that the load divided by the area will go beyond the strength of the material, and finally, the material, ductile material get fractured. So, yeah, this is your fracture point. F is this is a fracture point. This is not ultimate point, this is a fracture point. And after ultimate point, this portion u to f is called the necking. This is called necking. Now, this is some steels we are going to discuss. This is again sigma, and this is epsilon. So, this is high carbon steel. As we increase the carbon in the alloy steel, then the brittleness increases, and here this is having the high stress level beared by the material, but the strain as compared to others. As we move to the next, now this is a fracture point, here this is a fracture point. This is your medium carbon steel having the strength lower than high carbon steel, but it is having some more ductility. Then we will go to the low carbon steel. This is having a little bit lower strength, but fracture is here, and the elongation. You can compare the elongation from here. This is, and this is the largest. So, this is low carbon steel, and this is the cast iron where the carbon content is more than 1.5%. This is the brittle in nature. So, it fails before these. So, this is a cast iron, and this is a plastic material. Now, this is a special case I want to point out here. This is the stress strain diagram of a mild steel. This is sigma, this is epsilon and sigma. Epsilon, this is the only material where the proportionality limit, the yield point or the elastic limit and the upper yield point coinciding. This is the point, single point, and as soon as the loading reaches up to this, the corresponding sigma is represented by S by T. This is the strength at yield point, and as soon as you reach to yield point, the flowability will take place and there is a drop here. This is a drop in the resistance or the stress. So, this point is called the lower yield point Y L, and after that this zigzag, this area zigzag, this zone of the curve, this is nothing else. This is the rearrangement of the molecules or atoms, and this is called the strain hardening. And beyond that, strain hardening, the material will or mild steel will regain its resistance, power or the strength. The curve will start rising and reaches up to the ultimate point, and beyond ultimate point necking will start and it will start, it will fracture here. This is U. So, corresponding to this is called SUT, ultimate point in tension. So, this is the curve of the mild steel. Y L is the year, this is the lower yield point, and then strain hardening, then ultimate point and the fracture point, and this is necking. So, this is for today. This is the content I have covered, and in the next lecture I will discuss about the material properties and then move to the various types of the loads and the design against static load. So, thank you very much for today's lecture. Okay, thank you.